So we end this quarter with a brief introduction to differential equations. With the stuff you've learned so far in Calc 2, there's really two directions that we can go from here. One direction is into Calc 3, which deals with derivatives and integrals when you got more than one variable floating around. So multivariable calculus. And then there's the differential equations route that differential equations, as you'll see, is a very natural extension of Calc 2. So what is a differential equation? Well, the definition is a differential equation is an equation that involves a derivative or a differential. First of all, it's an equation, so it's got to have an equal sign. If something doesn't have an equal sign, it's not an equation. So you've actually seen some differential equations before. For instance, here's an example. If I gave you something like dy dx equals x cubed plus 3, saying the derivative of y is equal to this, well, that's a differential equation. It's got an equal sign. It's got a derivative in it. Other differential equations might look like, how about dy dx equals negative y squared. Okay. This looks a little different than that one. This one is something we've been dealing with all quarter. If I know the derivative of y is equal to this, can I figure out what y is? Yeah. This is giving the derivative of y in terms of y rather than in terms of x, so it just feels a little different. In terms of a differential, you did stuff already this quarter where we're doing integration by parts, for instance, where we had the u, the du, and the v, and the dv. Well, if I had dv equals, cosine x dx, then there's an equation. It doesn't have a derivative in it. It's got a differential on both sides. It's got an equal sign. This is a differential equation. There's all kinds of differential equations. These that I've given you, well, these two anyway, are what are called first order differential equations because the derivative involved is a first derivative. We'll see in a subsequent video when we start dealing with springs that we might end up with something like a second derivative involved, d squared y dt squared equals negative k times y or something like that. This now involves a second derivative of y and the function y. This is what's called a second order differential equation. Essentially, the order of the differential equation is the highest derivative that's involved. Okay? Now, that's the notion of a differential equation. Now I want to talk about what's the solution of a differential equation. Well, the solution of a differential equation is a function or a relation that satisfies the equation. I'll explain the or relation in a minute. If you take a look at that first differential equation I gave you here, where dy dx is equal to x cubed plus 3. If I take a look at the function y equals x to the fourth over 4 plus 3x, this is a function that when I plug it in for y, when I see does it satisfy this equation, well, does the derivative of y equal that? Well, try it, check it out. What is y prime? What's the derivative? Well, it's 4 times x cubed over 4 plus 3. Well, heck, that's equal to x cubed plus 3. So yes, the derivative of y is equal to x cubed plus 3. And that is a solution. In fact, you probably could have found that solution because you've been doing this type all quarter. Okay. On the other hand, if I take a look at that second differential equation that I had written down here, where I had dy dx is minus y squared, this one is perhaps not so easy to solve. Like, there's two questions that can be asked about solutions. One is to, hey, find a solution, and the other is to verify that something is a solution. And in this section here, 9.1 in the text, we're not expecting you to be able to solve the equations yet, but we'll at least would be able to ask you to verify that something is a solution. So, for instance, is y equals 1 over x a solution? So you plug it in on both sides. What is the derivative of 1 over x with respect to x? Well, that's equal to, well, it's x to the minus 1 power, so that's minus x to the minus 2 power, which I might write as minus 1 over x squared. And then I look at the right-hand side and I say, well, what's minus y squared? Well, y is 1 over x, so minus y squared is, well, minus 1 over x squared. Sure enough, those are equal to each other. So yes, y equals 1 over x is a solution to that differential equation. Now, if I just gave you the equation and said find a solution, well, that's a completely different beast, and we don't yet know how to do that. In fact, by the end of this quarter, yes, actually, we would be able to do that in the section 9.3 that we'll do later this week. So, the idea of a relation being a solution, you usually think of solutions as being functions, but sometimes you've got a differential equation that looks like, oh, how about dy dx equals minus x over y. Is that what I want? Yes, that's what I want. It turns out that the solutions to this thing are circles, in that if you take a look at x squared plus y squared equals a constant, right? Back in Calc 1, we had the notion of implicit differentiation. So if I implicitly differentiate here, so I'm thinking y is a function of x, so taking the derivative of both sides, I've got 2x plus 2y dy dx equals the derivative of that constant. Derivative constant is 0. Then I can solve for dy dx. So dy dx equals minus 2x over 2y, and the 2's cancel out, so it's minus x over y. So any circle centered at the origin satisfies the equation that dy dx is equal to minus x over y. The slope at any point here is the negative of the x-coordinate divided by the y-coordinate. This is not the graph function. This is, x squared plus y squared equals c. That's a relationship between x and y, but it's not a function. Yet I still would call this a solution. In fact, any one of these circles, a whole family of solutions here, any circle centered at the origin would be a solution to that differential equation. So sometimes you get functions, as in this example or in that example, those solutions were functions. Y is a function of x. Or sometimes you may end up with a relation where x and y are related to each other, but not in a function sort of way. Okay. Let's do one more example, or a couple more examples here, actually. These are just some of the even problems out of the book here. Let's ask the question, for what values of k is y equal the cosine of k times x a solution to, let's do a second order differential equation here, 4y double prime equals negative 25y. Okay. So again, I'm not saying solve this differential equation. I'm just saying find out when this is a solution to that equation. So if I plug that in, I want 4 times the second derivative of the cosine of kt equal to negative 25 times the cosine of kt. Oh, sorry, kx. I guess x is the variable here. It's interesting to me that when you read differential equations textbooks, they sort of alternate between x being the independent variable and t being the independent variable. And I mean, the same book will use both variables almost interchangeably. So sorry if I wrote a t when I should have been writing an x. So take a look. What values of k can actually make this work? So the second derivative, I got to do a little bit of work over here. If I've got y equals cosine kx, the derivative is going to be, well, there's a chain rule involved here. So k pops out. So negative k sine kx, do the second derivative. Another k pops out, so I got negative k squared back to cosine kx. So this second derivative, so I've got 4 times negative k squared cosine kx, that's my left-hand side. The right-hand side, well, that's just negative 25 cosine kx. So when are these two things equal to each other? Well, divide both sides by cosine of kx, and we've got that negative 4k squared is got to equal negative 25. So k squared is equal to 25 over 4, which tells me that k is plus or minus 5 over 2. So there's two values of k, which will make this function, y equals cosine kx, a solution to this differential equation. One more. Show that for any value c, y equals natural log of x plus c, all divided by x, is a solution to the following first order differential equation. X squared y prime plus x times y equals 1. Well, to say that to show that this is a solution means I'll plug it in and see that it's true. So, okay, I need x squared times the derivative of this thing. Well, this is a quotient, so the derivative is going to be, there's the denominator squared, the denominator times the derivative of the top. The derivative of the top is just 1 over x, minus the top times the derivative of the bottom. Well, the derivative of the bottom is just 1. So there's the x squared y prime plus x times y. X times, well, just plug the y in. So that's natural log of x plus c over x. And the question is that equal to 1? I don't know if it's equal yet. I need to show that it's equal to 1. So I'll put a little question mark over the equal sign for now, just indicating that I'm questioning, is it equal to 1? Well, I can do some algebra now. The x squareds are going to cancel out here. The 1 over x's leave me just with a 1. Sorry, the x and the 1 over x is 1. Distribute that minus sign through. Ln x minus c. Here, this x and that x cancel out. So that's just 1 times this. So I've got a plus ln x plus c. And is that equal to 1? Well, I got a minus log x and a plus log x. I got a minus c and a plus c. Yes, 1 is equal to 1. That any value of c will give you a different solution to this differential equation. Now, it's quite often the case that you have multiple solutions. In fact, usually you have infinitely many solutions to any particular differential equation. And to pick one particular solution, you usually need some sort of initial condition. I could say on this one, find the value of c, so that the solution passes through the point, I know that's not how you spell through, well, passes through the point, say, 1, 7. Right? So I know I've got y equals natural log x plus c over x, so I need 7 to equal natural log of 1 plus c over 1. Right? For 1 being plugged in for x, I need a 7 coming out. Natural log of 1 is 0. Oh, this was all really kind of nice. This is 0 plus c on the top and 1 on the bottom, so this says that c has to equal 7. So y equals natural log x plus 7 over x is the solution, the particular solution that satisfies this condition here. This is often called an initial condition. You got a differential equation with one bit of information that's going to lead you to one particular solution that satisfies both the differential equation and the initial condition. Okay. Anyway, there's a quick introduction. We will look at some more things in the next video.